Hello everyone, welcome to a lecture on digital logic design. I am Dr. Vilayat Khan, and this lecture I will talk about two major components of digital systems, in particular digital computers, registers and memory. A register is a group of binary storage cells suitable for holding binary information. In a register, in an n-bit register, there are n binary storage cells which stores n bit of binary information. For example, in an 8-bit register, there are 8 binary storage cells which stores 8-bit of binary information. Similarly, a memory unit is a collection of storage cells, just like registers, but in addition there are some associated circuits which are required to or responsible for transfer of information in and out of the storage cells. Similarly, just like registers, memory units are also a very important component of digital systems. The memory cells or the binary storage cells in both in register and memory units are actually created from flip-flops. One of the most popular flip-flop used in sequential circuit is a D flip-flop. A D flip-flop is a sequential circuit that consists of 5 NAND gates. This part of the D flip-flop is called RS flip-flop, or implemented with the NAND gate. In this part of the flip-flop, this input is called set and this input is called reset, and the outputs of the flip-flop are called Q and Q prime. These outputs are actually the outputs taken from the flip-flop, or also it can be it can represent the current state of the flip-flop, whatever the flip-flop maintains or contains. That can also be taken from these outputs. The fact that Q and Q prime are complement of each other, it represents a valid state of the flip-flop. If these two outputs are not the complement of each other, then such a state is an invalid or indeterminate state, and it should not be reached. We should not write any input that would take the flip-flop to an indeterminate state. In addition to this basic RS flip-flop, where this input is R and this is the S input, there are two additional NAND gates connected to the basic flip-flop that connects a clock pulse with the basic flip-flop. This clock pulse plays an important role here. When the value of the clock pulse is high, when it is 1, whatever the input that is provided here can affect the current state of the flip-flop. But when it is 0, it doesn't affect the current state of the flip-flop. There is a single input called D input, and this D input is connected directly with this flip-flop, this NAND gate, and its inverted version is connected with NAND gate 4. We assume that the clock pulse is 1, and then we can see that when the value of D changes, how can it affect the current state of the flip-flop, provided a current state is given, and how can it affect the current state so that we can get to a next state. So given the current state of the flip-flop, which is represented with Q, we can determine the next state, which is normally represented with Q t plus 1 when an input is given, and we assume in all these cases that the clock pulse is 1. Here is the characteristic table that describes when the input D is changed, and provided we have the current state Q, we can determine the next state of the flip-flop, which is represented with Q of t plus 1. Let me consider this first case where the current state Q is 0. We don't consider Q prime in this table because Q prime is always the complement of Q. So we can take it from inverting the value of Q. So Q is the current state of this flip-flop, and we give an input D here, and we always assume clock pulse is 1, so we don't consider that in this characteristic table as well. So we just consider the current value D and the current state Q, and we can see that what would be the next state given the current state and the current input. So when the current state Q is 0 and we give an input with D which is equal to 0 in this case, this 0 comes here and it becomes 1 here, because clock pulse is 1, it is 0, so regardless of this clock pulse, this value is 0. So from the NAND gate property we know that the value S here, the S input is 1. Similarly, this 0 becomes 1 here, and when both of these inputs are 1, so we get 0 here. So the R input is 0 and the S input is 1. Here, when we follow this R input to NAND gate 2, we know that at the inputs, when one of the input at the NAND gate is 0, we get 1 here. So Q prime is 1. This one is fed back to NAND gate 1, as the other input is also 1 and this input is also 1, so we get 0 here. So Q is 0. So when current state Q is 0 and we give an input D, we get the next state 0, which is here. A similar explanation can be given for all other combination of inputs, and here is the complete description of all the possible cases. This can be described on a K-map, two variable K-map, and we can derive a characteristic equation for the next state Qt plus 1, as we have a single 2 square group. These empty squares represent the minterms which are not included in this equation, and when we group these 2 squares we get D. So Qt plus 1 is equal to D, and which is also clear from this characteristic table. Look, this Qt plus 1 column is exactly the same as D, so we could derive the Boolean equation of Qt plus 1 directly from the characteristic table because they are the same. So in simple words, when the clock pulse value is 1, whatever is provided here at the D input, that becomes the next state of the flip-flop. In other words, whatever is given here, that is stored on this flip-flop. So we provide 0, we store 0. We provide 1, we store 1. This is the graphic symbol of the D flip-flop. This is the Q prime output, this is the Q, this is the input, and this is the clock pulse. Now, as we saw in the definition of a register, which is a group of binary storage cells, we can combine multiple D flip-flops in this way. This is a 4-bit group, and as each D flip-flop can store a single bit, so each D flip-flop can serve as a storage cell. So we have 4 storage cells here, and when we have 4 storage cells, then it becomes a register, and the size of this register is 4. Each storage cell or D flip-flop in this case can store a single bit. We have 4 storage cells, so this is a 4-bit register. The D inputs are connected to the inputs coming from some data. For example, it can be the data bus. So this is input 1, input 2, input 3, and input 4. When the clock pulse becomes 1, at that moment, whatever is available at these input is stored on these flip-flops, which can be read or taken from these outputs A1, A2, A3, and 4. So when a clock pulse is provided, whatever has been provided at these 4-bit inputs are stored on these 4 D flip-flops. Or we can say that this data or this binary group of binary bits are stored on in these 4-bit register, in this 4-bit register. So this is a 4-bit register, and we can store 4-bit of binary information in this register. We can add some additional circuitry to control the operation of this register. This is again D flip-flop, but we add some additional control. For example, here we have a load control. This load control controls when to write data on this register. We have the same 4 inputs, I1, I2, I3 and I4, and the same number of 4 outputs, A1, A2, A3 and A4. So this load input is connected to the D input, but through these 2 AND gates and an OR gate. When this load is 0, this 0 is connected with this AND gate, which takes an input I1. So when load is 0, regardless of the value of I1, we get 0 here. Similarly, when this load is 0, regardless of the value of I2, we get 0 here. And similarly for other 2 inputs as well, I3 is 0 here, I4 is 0 here. So one input is to these OR gates is 0, and as load is 0, we get 1 here. So these AND gates, this AND gate, this AND gate, this AND gate and this AND gate, will get one of the input as 1, but each gate has a second input which is taken from these outputs. A1 is connected here, A2 is connected here, A3 is connected here, and A4 is connected here. So one of the input of these OR gates is 0, because load is 0, so we get 0 here. So this output is totally dependent on whatever we have at these outputs, whatever the value of A1 is, A2, A3 and A4. So if A1 is 0, we get 0 here. If A1 is 1, we get 1 here. And whatever is provided here, that is stored on this flip-flop. Similarly for all other flip-flops as well. So whatever is stored on A2, that is fed back here. If it is 0, we get 0 here. If it is 1, we get 1 here. Why? Because the other input is always 1. Because load is 0, so we get 1 here. So whatever is stored on A2, we get that bit here. And if it is 0, we get 0 here. If it is 1, we get 1, because the other input is 0. Similarly for all other OR gates. So when load is 0, we get here the value of this output. If the value of A1 is 0, we get 0 here. If it is 1, we get 1 here. Similarly, if A2 is 0, we get 0 here. If A2 is 1, we get 1. And whatever is provided at the D input of these flip-flops, that is stored on this flip-flop. So in other words, when we provide 0 at the load input, these inputs will not affect the state of these flip-flops, but in fact the same state is repeated. The same states are fed back and are restored on the same flip-flop. And this is the role of this feedback. Because in the D flip-flop, there is no input that can maintain the current state. So this feedback is used to refresh its current state when the load is 0, and these inputs cannot now change the state of these flip-flops, but in fact the current state of these flip-flops is maintained. So whatever information has been stored in this register, it is maintained when the load input is 0. On the other hand, if the load input is 1, we get 0 here. So this 0 will invalidate or make the outputs 0. Whatever these A's will return here. This 0 will make the output here as 0. So it will not affect whatever is provided at these inputs. When load is 1, this line will make one of the input of the upper AND gate as 0. So we will get 0 here for the upper AND gate. So what we will get here, we will get exactly whatever I1, the value of I1 is. If load is 1, we get 1 here. So this one is connected with this AND gate, and I1, if I1 is 0, we get 0. If I1 is 1, we get 1. So in simple words, when load is 1 and we provide an input here, that input becomes the next state of these flip-flops. In simple words, when the load is 1, whatever we provide at these inputs, that information is stored on these 4 flip-flops. So load basically controls when we want to write data on the register. If we are not interested to write data, we just provide 0. Even if then you provide the clock pulse or the data here, nothing will be stored on the flip-flop. The same already stored information will be retained. But when it is 1, then whatever you provide here will be stored on the flip-flops. So the clock pulse role is the same as before, but another important input is the clear input. Normally, when a digital system is turned on, it is quite possible that the state of these flip-flops is indeterminate, and in that case the next state cannot be clearly defined. So to make the state in a clear state, this input is connected to all the clear input of the flip-flops. So what this clear input will does, when a 0 is provided, it will clear the state of the flip-flop, and 0 will be available at the output of all these flip-flops. Now when 0 is available, these flip-flops are now ready to be updated with new data here. So when clear at the initials, when the digital system is turned on, it is cleared, and after that whatever you provide here, it is stored on the flip-flop. So this load controls when to write, and this clears the current state of these flip-flops when the digital system is initially turned on. Now let's talk about memory unit. As I said, a memory unit is a group of storage cells. In addition, there are some additional circuitry or control circuits which are responsible to take information in and out of the memory unit. A memory unit in general will look like this. In the memory unit, there are n group of storage cells, and each group of storage cell stores m bits, or there are m storage cells in each group. As each storage cell can store a single bit, and the number of storage cells in a group is called a word. So there are n words or n groups, and each group contains m storage cells or m bits of information, and each group is also called a word. So if there are m bits in the group, then there are m bits in the word. So there are n words, or in simple words, n memory locations, and the width or the size of each location is m bits, and this is also called a word. So the width or the size of the word is m, or each word consists of m bits. M can be 8, M can be 4, M can be 16, it can be 64. So the number of bits in each word depending on the memory unit. So there are n words. There is an additional register called the memory address register, or in simple MAR, memory address register, and there are input lines connected to this memory address register, and these input lines, which is also called input addresses, are equal to the number of storage cells in this memory address register. And this memory address register consists of 10 storage cells, then there would be 10 input lines or input address lines connected to this memory address register. Now this register and these lines provides the address of the word in this memory unit. If there are n address bits here, then there are total 2 raised to power n words in this memory unit, and each combination of these n bit address is equal to a decimal value, which is the number of word in that memory unit. For example, if there are 32 words or memory locations in this memory unit, then the memory address register should be of at least 5 bits, because 2 raised to power 5 is equal to 32. So 5 bits of memory address is sufficient to uniquely identify these 32 words or 32 locations in this memory unit. So the memory address register stores a memory address, and that address will identify a specific word in these n words, and that n-bit address is provided to this memory address register through this input address bus. Here we have a memory buffer register. This memory buffer register, or MBR, will temporarily stores a word of data to be written to a memory location or to be read from this memory. When a word of data is to be written onto this memory unit, that word of data comes through this input bus to this memory buffer register, and then is written to a location addressed by these bits in the memory address register. So this address will identify a location where this data in the memory buffer register is written to that location. In the read example, a memory address register will identify a memory location, and a word of data is read from that memory location and is moved to this memory buffer register, which is taken out to the microprocessor or any other component in the digital system. So this memory buffer register is used in storing the data in the memory or taking the data out from the memory unit. And which operation should be performed, whether the data should be written into the memory unit or taken out of the memory unit, this is called read or write operation, and this is decided by the control signals. The control signals, read and write control signals, are provided to the memory unit, and that will decide whether the data here to be written to this location or to be read from that location. So these control signals will choose one of these two operations, read or write operation. So we have address from here, we have data provided here, and the control signals provided here. In a broader spectrum, in a digital system or digital computer, normally this address is connected to the address bus coming from the microprocessor, and these in and out lines are connected to the data bus of the microprocessor. And similarly, these control signals are coming from the control pins of the microprocessor. This is a simple example with some content. Let's suppose this is a memory unit, and this memory unit consists of 1 kilobyte of memory. 1 kilobyte of memory can be organized in different way, but in this example the memory is organized as the following. We have 1 kilo words or 1 kilo group of memory storage cells, and each group consists of 8 storage cells, or in simple words, there are 1 kilo in binary system. 1 kilo is equal to 1024. So there are 1024 words, and each word consists of 8 bits. So there are 8 memory cells or storage cells, and each cell is responsible to store a single bit. In decimal system, each word is numbered as 0, 1, 2, 3, 4, 40, 41, 42, 43, and until 1023, because we start from 0. Here we have 10 bit of memory address register, because 10 bits are sufficient. 2 raised to power 10 is equal to 1024. So to address these 1 kilo locations uniquely, we need a 10 bit address. So the size of memory address register should be or must be 10, because it is sufficient to store 10 bit of memory address. Similarly, as the word size is 8, each location can store 8 bit of binary information. So whenever we want to write 8 bit one word or 8 bit of data, or when we want to read 8 bit of data, so the memory buffer register must be 8 bit, because it can be larger, but that is not a good solution. So an 8 bit register, memory buffer register, is sufficient to store the 8 bit data that is to be stored in a location or to be read from a location. And the location address is provided by this memory address register, which is 10 bit register. So this 10 bit address is sufficient to uniquely identify these 2 raised to power 10 memory locations. So there are 2 raised to power 10 memory addresses. In this example, let's suppose the memory address register contains a binary value which is equal to 42 in decimal. So this 42, the memory location 42 or the memory word 42 has this 8 bit information. After the read operation, this 8 bit value is moved to the memory buffer register, which will later on be sent through the data bus to the microprocessor or any other component. In case of the write operation, whatever the memory buffer register contains, here in this example, this is an 8 bit value that is written to this location 42, and this location 42 must be specified by the memory address register. So in the read operation, an 8 bit value is taken out of the memory unit and stored in the memory buffer register, and in the write operation, an 8 bit value is taken from the memory buffer register and stored on the location provided by or identified by memory address register. As we are talking about the memory cells, and registers and memory units. Now let's see how a memory cell look like in these registers and memory units. This is a memory cell implemented using SR flip-flop. Here in the SR flip-flop, this is the S input, this is the R input, and this is the state of the flip-flop. When a 1 is provided at this input S and a 0 is provided at this R input, then this combination 0 here, 1 here, it will set the flip-flop. A 1 is stored here. And when a 1 is provided here and a 0 is provided here, it will reset the flip-flop. That means the value of Q becomes 0. So this is the simple operation of the RS flip-flop. And remember that this is a simple RS flip-flop implemented with NOR gates. And there is no clock pulse. But there is some additional circuitry, AND gate, two AND gates, these two inverters. Here, this is a read or write input. So a 0 or 1 will decide whether a read operation is desired or write operation is desired. Here we have a select input, a single bit select input, and here we have a single bit input, and here we have the only output. So first let's consider the select input. When this is 0, when this select input is 0, this 0 is connected to one of the inputs of these two AND gates. And as we know, when one of these inputs of these AND gates is 0, we get 0 here. 0, 0. So when a 0, 0 is provided at the two inputs of the RS flip-flop, the current state of the flip-flop is maintained and nothing is changed when the input is provided. So when the select is 0, this input will not affect the current state of the flip-flop. So whatever you provide here will not change the current state of the flip-flop. So in simple words, when select is 0, this flip-flop is not selected. It is not functional. Nothing can be written to it. And similarly, nothing can be read out from this flip-flop. Why? Because this select is 0. So this AND gate will make the output 0. So when the select is 0, input cannot change the current state of the flip-flop and nothing can be read out from the flip-flop. So because the select is 0. When the select is 1, one of the input of these AND gates, this AND gate and these two AND gates is 1. Now the output and the input can change or can change the state by changing these values. For example, if we change the input, we can change this R input and S input. But there is another input we have to consider that as well. And simple, when select is 0, input cannot change the current state and output is always 0. When select is 1, input now can change and output can read the current state, but we have to look for the read and write control signal as well. When it is 0, when this input is 0, this becomes 1 here, and this will make one of the input of these two AND gates 1. So we assume select is 1 and this is 0. So this 0 will make the second input of these AND gates as 1. So what remains is the input. So this input can now change the current state of this flip-flop. If it is 0, we get 0 here and we get 1 here. So it will reset the flip-flop. Means it will store 0 on the flip-flop. When we provide 1 here, we get 1 here, we get 0 here. So it will set the flip-flop. Means 1 will be stored in the flip-flop. So when it is 0, when this read-write input is 0, it will become 1 here, and then we assume select is 1. So whatever we provide here, that can be stored here. So that becomes write. So when this read write is 0, that means a control signal write is provided here, and we can now write on this flip-flop provided the select input is 1. Similarly, if it is 1, then it will become 0, and the input, this input will be ineffective because one of the inputs to these AND gates is 0, because we provided 1 here, so that becomes 0 here due to the inverter. And when 0 is provided here, we get 0, 0, and 0, 0 means keep the current state. So this input now cannot change the state of the flip-flop because we have provided 1 here, and that 1 kept R and S input 0, 0. So it will keep the current state of the flip-flop regardless of the input. So when read write signal, when it is 0, we can write. When it is 1, we cannot write, but we can read. How? When it is 1, this input to this AND gate is 1, the select is 1. So whatever the state Q is here, the output is equal to that value. So when write is 1, we exactly get the current state or the value of Q as the output. So we can now read. So when read write input is 0, we can write. When read write input is 1, we can read. When the select input is 0, nothing can be written to or read from this memory cell. When the select input is 1, we can write or read from this memory cell. So there are 3 inputs and 1 output of this memory cell, and this memory cell is implemented with simple SR flip-flop without clock pulse. This is the symbol block diagram of memory cell. This is the select input, this is the input, this is the read write, and this is the output. Now a single memory cell can store a single bit of information. Now if we organize a number of such memory cells or bit cell, we can design a random access memory. This is a simple example of random access memory. Now this memory is a 12-bit memory consisting of 4 words, and each word consists of 3 bits. Now remember the 3 inputs of the memory cell or the bit cell and 1 single output. We need a 2x4 decoder to address 4 memory locations. This is 1 memory location, this is another memory location, this is another memory location, and this is the last memory location. So we provide the address input to the 2x4 decoder. We have 2-bit address input, and we will get 1 output here. So one of these output will be 1 at a specific time. When 0, 0 is provided, the 0 output will be 1. When 0, 1 is provided, this 1 will be, D1 will be 1. And when 1, 0 is provided, this D2 will be 1. And similarly D3. So whatever the address is provided, it will enable one of these words or these group of binary cells. When 0, 0 is provided, this group will be the select input of these cells will be 1. When 0, 1 is provided here, the select line of all these cells, these 3 cells will be 1, and similarly for other combinations as well. Now assuming a particular group of cells is enabled, and the data is provided here. 3-bit data is provided here. This is the input coming from the data buffer register or memory buffer register. So when a particular group of cells is selected, the read or write control signal will enable a read or write operation on that group of cells, and accordingly the data will be written to that group of cells or will be read from that group of cells as the data output. The data output combines the outputs from each group through these OR gates, and the data input are connected to the input of each binary cell. So with this organization, where we have 4 words and each word can consist of 3 bits, we can store 12 bits of binary information on this random access memory. There is an memory enable pin as well that will just disable or enable this decoder, and through this enable or disable we can enable or disable the whole random access memory. Thank you.